Guys, so this whole series right here is going to be about how to deal with ice tables. Okay? So here's the thing. We got to come up with a reaction that we can model this off of. It's going to be A plus B equals C plus D. It's going to be a long video, so I got to make sure I make it in 10 minutes. So I'm going to move a little fast, but hopefully I don't confuse anything by doing so. So you're going to have S. That's going to be your substance, your initial, your change, and your exit. Okay? And we're going to come up with the equations for concentrations for each and every reactant and product. So the first thing you got to do is you got to find out what your limiting reagent is, because that's what your conversion is going to be. You can have conversion in terms of B, conversion in terms of the converted of A. So let's see. So I'm going to come up with an example. I'm going to add a coefficient in here to make it a better example. Let's say that's 2. So if I had A equals 1 and B equals 1.5, what's going to happen? Which one's our limiting reactant is really what I'm asking. Well, if I feed in 1 mole of A, I'm going to need 2 moles of B to complete that. I only have 1.5. I got less than what's needed, and therefore B is the limiting reactant, right? So let's put our substance, A, B, C, D. So what's our initial conditions, right? So I'll do it in terms of molar flow rate first. Here you got Fa sub naught, Fb sub naught, Fc sub naught, which is usually 0 because usually you don't have products to begin with, but I put Fc sub naught just in case. Fd sub naught. Now your change. Now we're going to do conversion in terms of B because that's our limiting reactant, right? Okay, so B is our limiting reactant. So what we're going to do is we're going to say, okay, well down here, negative FbO times X. And that makes sense because if you have the initial amount of B and the amount of B converted, it's telling you how much B left when you multiply this. This will give you moles of B that left per unit time. And if you subtract that from this, it's going to give you what you're left over with. Right? So if you put those two things together, FbO minus FbOx, better written as this, that's what you got. And that's going to be equal to Fb, right? So let's do the same thing with FaO, but there's a subtle little difference here. You got to go like this. Over A, negative A over B, FbO, X, right? The reason you do that is because X is in terms of B, so when you multiply these two things together, you're getting the amount of B that left. And using the stoichiometric coefficient like this, it's going to tell you how much of A left. And then you subtract that from the initial A, and you're going to have the A left. In other words, did I erase something? Yeah, I did. Sorry about that. Yes, so you're going to get this left over. And that's all going to be equal to Fa. Now we can do the same thing down for C and D. Another little cell difference because C is forming and D is forming and not disappearing like in the case of A. What you're going to get is you're going to get C over B, FbO, X. And again, everything's in terms of B really because you're dealing with the conversion of B and B is your limiting reactant. So you got to do this whole analysis in terms of that. So then here you get FCO plus CB, FbO, X, right? And that's going to be equal to Fc coming out of the reactor. And same thing for this guy. All right? So then this would be FdO plus D over B, FbO, X equals Fd. So now, if you look at it, you got equations for Fa, Fb, Fc, and Fd in terms of initial conditions and stoichiometric coefficients and conversion. So can you do the same thing, not with the molar flow rates, but can you do the same thing with concentrations? And you bet, yes, you can. So I got to move a little fast so I don't run out of time. I'm going to do the exact same thing. Now, keep in mind that B is our limiting reactant, right? Due to our analysis up here. Okay, so same thing goes. But this time you're using concentrations, right? So you see, these things aren't that hard to create, as long as if you can memorize, in a sense, just to make it more, make yourself more proficient, the coefficient in front of FbO. So I always start with the limiting reactant first. So over here we're going to say minus CbO times X, right? And this would be minus A over B, and then the same thing is below, right? And then this would be C over, not over B, or not over A, over B. CbO times X, D over B, C BO times X, right? Now you just put them together. The E is probably the easiest part, this part, the exit or ending. So initial, change, substance, exit, right? Now, okay, CaO minus A over B, CbO x, CbO minus CbO x. Again, this is Cb, this is Ca. Now CCO minus C over B. Oh, no, not minus, plus. Nearly made that mistake. Cc. And over here is initial D, concentration, plus D over B, CbO times X equals Cd. So these will be your equations for your concentration sometimes later in the reactor. Now in the next video, what I'm going to go over is I'm going to go over the relationship between the rate of reactions, right? Because when you're doing this kind of analysis, and I give you the reaction rate of B or C or of D, you have to be able to put it in terms of the one that you want. So in other words, the relationship we're going to discuss in the next one is going to be this relationship here. Very important relationship. If I gave you the reaction rate of D, let's say, of the formation of D, you can now get from that, put an arrow, not an equal sign. If I give you the reaction rate of D, you can convert that into the disappearance of A, and vice versa, for any which one you want, using stoichiometric relationships like this. I'll give you the proof for this so it makes more sense. And I'll see you guys in the next video. I hope this helps, these ice tables, and they're very useful, and you'll probably be using them all the way through the class after chapter 4. Alright, see you guys later.